Math 265A, Cuesta College. I'm Joe Vasta, and we're going to cover section bug 3. So before we get to the bug, let's do a standard problem with lines. You have f of x, it's a function, passes the vertical line test, there's a picture of it, and it passes through the points 1, 3, right here, and 4, 10. The first question is find the slope of the secant line. The second question is find the equation of the secant line. So, the slope of the secant line. What is the secant line? Let's draw the secant line in red. The secant line of a curve is a line that connects 2 points on the curve, and the secant line looks something like this. Connects those 2 points. So we're trying to find the slope of that secant line. Basically, we're just trying to find the slope of a line going through those 2 points. That's really what we're doing. But that's an important skill to know. So the slope, so this is part A, is denoted by m, which is rise over run, which is also, it has a formula. The formula is y2 minus y1, that's the rise, all over x2 minus x1. The points that we have happen to be 1, 3, so let's call this x1, y1. There's point 1, and point 2 is x2, y2. I'm going to plug those into this formula here, and we have y2, which is 10, minus y1, which is 3, x2 is 4, minus x1, so minus 1. So this gives me 7 on top and 3 on the bottom. So this happens to be the slope of this secant line. Now, another way we could have done it is we could have just done rise over run, and if I had grid paper here, it would have been better, and you could say I'm going up 1, 2, 3, 4, 5, 6, 7, and then running over 3 to the right in the positive direction, 1, 2, 3. That gives me 7/3. Part B, find the equation of the secant line. Okay, so now what I have is I have the slope of 7/3, and I have a point of 1, 3. Now there's a few ways of doing this. Some teachers would say, well, use the point slope form, and that's cute. That will get the problem done. What I'm going to use is just this, y equals mx plus b. I know what m is. M is 7/3. Now before we move on with this, and this is just a review, there are 4 letters here. 4 letters in this equation. Y, M, X, B. 2 of the letters are variables. That would be X and Y. And 2 are constants. The constants are M and B, B being the y-intercept. So that's what we have here. We have 2 variables, 2 constants, which make up the 4 letters. Well, I know what one of the constants are. I know that M is 7/3. 7/3 X plus B. So really I just have to find the other constant, and then I have found the equation of the secant line, which is the red line there. To find B, one way to do it is to plug the point 1, 3 in for x and y. So this is just one instance, one point that's on the line. I could plug the point 4, 10 in there and get the same results that I'm going to get right now. So y is 3. It's a variable, and in this case we have 3 equals 7/3, and then here's x1 plus b. 3 equals 7/3 plus b. I suppose I should just use another piece of paper here, and I probably should have done that earlier. Okay, so I'll write this up here. So 3 equals 7/3 plus b. So I'm going to solve for b now. We can work with the fractions, or I'm going to just clear the fractions out by multiplying by both sides of the equation by 3. So it looks like I have 9 equals 7 plus 3b. So multiplying everything by 3. 2 equals 3b, subtracting 7 on both sides. So it looks like we divide by 3 2/3 equals b. So I have the m, I have the b, I have found the two constants. So the equation of the secant line looks like this. Y equals 7/3 x plus 2/3. And that answers question B, finding the line. Now this stuff comes from an algebra class, but from time to time we forget things, so this is why I did this problem here. And somehow the secant line between 2 points is going to be very important when we talk about bugs on a number line. So let's move on to the next thing. So now we're going to get into the bug 3. So there it is. Suppose a bug is moving on a number line. So I'm not showing the number line this time, I'm just describing it. The time is measured in t. That's like on the x-axis, so now it's the t-axis, and the position is s. And f of t equals s, so that's the function f of t. The output is going to be the position on the number line, the input is the time. And we're given this picture, so this is the given. We have a picture of a parabola, and this kind of describes the bug's motion on a number line. Now in bug 2, I believe it was bug 2, we took a picture like this. It could have been bug 1. I think it was bug 1 actually. We took a picture and we drew the diagram for the bug. Now we can do that on this one, and maybe I'll end up doing that after I answer some of the questions. Let's go ahead and answer some questions here. So we'll move this up. This is going to be a little tricky because if I was in the classroom, I'd have a lot of board space. Anyway, I think we can do this. It says, where is the bug at 1 second? So 1 second happens to be time. So this is t. T is 1. So where happens to be position. So this is position. So we're actually asked to find an s value given a t value of 1. So the t value of 1, I go to the t axis and find 1. 1's right there. And I look up or down until I see the function. And I look down, I see the function right there. And this point is the point 1, comma, -1. So when time is 1, that's the input. The bug is at -1 on the number line. So the answer, where is the bug at 1 second? At -1 feet. So you'll get problems like that in your homework. Where is the bug at 1 second? -1 feet. Next question. When is the bug at 3 feet? So 3 feet happens to be an S value. And it says, when is the bug at 3 feet? That is T. We are looking for T when S is 3. So instead of going to the t-axis, like we did in the last one in finding a value and looking for the function, we're going to go to the s-axis because they've given us that s is 3. So they're giving us the output and they want to know the inputs. And at s is 3, we actually look along this horizontal line, and there are actually 2 points. Look, this point right here is 0, 3. And this point over here is -2, 3. So those are 2 input-output pairs where the output is 3 feet. So it says, when is the bug at 3? Well, there are actually 2 times -2 seconds. And the other one is 0 seconds. And we talked about this maybe in a previous video. It does make sense to have negative time. -2 seconds is like 2 seconds ago. So that's what we have there. Now, the next question, it says, what is the bug's displacement over the time interval? -2 to 1. Now, when we have a bug diagram, okay, so hopefully that's in the picture. When we have the bug diagram, we can just count the displacement. It's a snapshot. At -2 seconds, the bug is somewhere in the number line, and then at 1 second, the bug is somewhere else, and then we say, oh, well, how much displacement was there? Was he to the right or to the left? And so that's how we do it. But there was a formula that we used, and the formula, I'm going to move this up a little so we can fit this, said something like this, where you find the displacement by going f of the end time minus f of the beginning time. Okay, so we really have to know how to evaluate functions using their graphs. F of 1, we kind of already explored that. Here's 1. F of 1 is -1. Minus, okay, so f of 1, there's the minus sign. Now f of -2, well, -2 is here. The time is -2, the output, the position is 3. So we have a 3 there. I'll put parentheses around these here. Okay, so there's f of 1 is -1 and f of -2 is 3. So this gives me -1 minus 3, -4. So our answer is -4 feet. I'm going to check to make sure everything is in the camera range. Perfect. I'm going to box my answer here. Okay, my next question is the following. And so these are questions that we saw from the previous bug. I think we did displacement in bug 2. And here they're asking, what is the bug's average velocity over the same time interval from -2 to 1? Now, the average velocity is really the displacement over the time. And the displacement we found in the last problem, -4 over the time. Well, how much time is in this time interval? Well, it looks like 3 seconds. Now, technically, we should be saying -4 feet over 3 seconds. And so our answer is -4/3 feet per second. Okay, Now in bug 2, I also mentioned, the formula for this is we can take the displacement formula. So we're done with this. We're just looking at this. As a math teacher, I have to make things more complicated because, that's just the reputation I have to live up to. The displacement is f of 1 minus f of negative 2. This is all over. And then the time you can get by going 1 minus negative 2. And so, of course, this f of 1 minus f of negative 2, we already did that calculation. That's where we're getting the negative 4. And then on the bottom we have 3. So it's just the same way. But this, what right here, should remind you of something that we did at the beginning of this lecture. And perhaps, let me go ahead and show this. This is sort of a rise over run. Look at this. y2 minus y1, x2 minus x1. So this kind of reminds me of this right here. I mean, these are x values, or actually those are t values, and then these guys right here, f of 1 and f of negative 2, those are s values or y values. So this negative 4/3, not only is it the average velocity, but it has something to do with the graph. Remember, this rise over run gave us the slope of the secant line. So let's take a look at this right here. Our time interval was from negative 2 to 1. So the points that we're looking at were these points right here. And you can actually draw the secant line on that one. And it looks like that. Let's look at the slope of the secant line. If I count from this point to this point, I go up 1, 2, 3, 4, and I go in the negative direction, 3. So rise 4 over run, 1, 2, 3, negative 3. That's 4 over negative 3, or negative 4/3. So what significance is this? If you're given a position function, the picture of a position function, and you want the average velocity, physically what that is, it's the slope of the secant line going through those 2 points. So why don't we go ahead and label that. This guy right here is the slope of the secant line. And it's not like if we were asked this question again, we would then do it using a picture. I'd probably still do it the same way, but we want to make this realization because this is going to help us with calculus. So if they wanted to know the average velocity on the time interval from negative 1 to 1, we'd have this dot here, we'd have this dot here, and then I would look at the average velocity would be the slope of that right there, which I would just do algebraically here. Okay, question E. When is the bug at rest? Rest means velocity is 0. Now that might not mean a lot to you, but what it just means is the bug is not going to the right and is not going to the left. And we talked about this in an earlier bug lecture. The bug is at rest when you are looking at the bottom of a valley or the top of a hill. So the bug is at rest right there. So let's go ahead and in green we'll do that. This is where the bug is at rest. That's where the bug is turning around. And they're asking, when is the bug at rest? So when, they're looking for a time. And so let's find the coordinates of this point here. The coordinates of this point happen to be negative 1, 4. So -1, 4. The first coordinate being the time. So when is the bug at rest? The bug is at rest at time -1 second. Which sounds funny. You could say, you know, the bug was at rest 1 second ago. The next question says, where is the bug at rest? So where happens to be S, the second coordinate. And the bug is at rest where? At 4. 4 what? 4 feet on the number line. Okay, so look, the first coordinate of this vertex, or this maximum, is -1, and the second coordinate is 4. The last question is, what is the bug's total distance traveled over the time interval -2 to 1? Okay, there's a few ways of doing this. The quick way for total distance traveled is, here's the bug. One way of doing this, the distance traveled is measurement along the s-axis. So when you're going from here to here on the graph, let's go ahead and count. So maybe I'll use another pen. So as I'm going up here, I go like this. So I travel the 4, and then I come back down like that. So I've traveled 1, 2, 3, 4, 5, 6. Oh, let's try this again. 1, 2, 3, 4, 5, 6. Now, some of you are like, well, Joe, that was pretty confusing. So let's go ahead and do the other thing that I showed you in a previous lecture. Here is the number line that the bug is traveling on. And yes, it's going vertical. And what's happening is, starting right here, you're there, you're 3 on the number line, and you go up to 4, and then you go down to right here. So, and this is of course going to be time 1, and then over here was time -2. So that's what the bug's doing. And so if you want to do the total distance traveled, you go 1, 2, 3, 4, 5, 6. So the answer is 6 feet. And that's gotten by counting. And we'll find better ways of doing this. The other thing that I wanted to finish this off with is the bug diagram. The bug diagram actually, here's the number line the bug is traveling on, and I'm going to put a 4 there, and a 0 there, etc. So what the bug is doing, we could take a look at this part right here. The bug starts at 3 and he kind of goes to 4, turns around at 4 and goes back toward the negative direction. Now I'm going to make this a lot longer because this is the whole travel of the bug, the whole parabola. And so the bug is going like this. I'll put a few arrows on here so you can see what the bug's doing. And then his turnaround point was at time -1. And so this is what we did, I believe, in bug 1, is we took pictures and we drew the bug diagram. Yeah. So that completes these questions here. A lot of the main things that we saw is total distance traveled, average velocity, displacement, rest is important, and then these were just to make sure we know what we're doing. Okay, we're going to do some similar problems. You know, like this one, the bug's motion was given with a graph, time on one axis, position on the number line, you know, where you're on the number line on the y-axis. We're going to give you the next problem. I'm not going to give you the function picture, but I'll just give you a regular function that says f of t equals something. That will be problem 2. so let's go ahead and do that. So, same situation. Suppose a bug is moving on a number line. Time is measured in seconds. It's t. Position is measured in feet from the origin. That's s. And f of t is the function where the input is time and the output is the position on the number line. So there it is. And this looks like another parabola. Sure, we could graph it and whatever, take a look at a parabola that gets shifted up 3. But to answer these questions, we don't have to do that. Things are going to be a little more algebraic on this. Okay? So it says, where is the bug at 7 seconds? So the thing we want to realize is 7 seconds is a time. And they're asking us where, which is s. Now, you could also say, oh, this f of t, you know how we replace f of x with y? Well, this f of t can be replaced with an s. So if it makes you a little happier, you can say that s equals t squared plus 3. That's the same thing. So they give us t equals 7. Let's plug it in there. So for this problem, I'm going to say like s equals 7 squared plus 3. 7 squared is 49 plus 3, which is 52, and we got to do our units. So where that's measured in feet in these problems. So that's where the bug is at 7 seconds. Now, the function notation is sweet because another way we could have done this problem is we could have just said f of 7. That's kind of what this is here, and so that's a nicer way of writing it, but this is just as good. Okay, part B. When is the bug at 10 feet? 10 feet happens to be a position, s. And they're looking for time. So what we're going to do is we're going to use, let me put a box around this up here so we don't lose it. Now we're going to put 10 in for s and find out what t is. So this is 10 equals t squared plus 3. I'm going to subtract 3 on both sides, so I end up getting 7 equals t squared, or t squared equals 7. Okay, so I'll move up here. I'm going to do the square root property, where I take the square root on both sides. I get t equals, and you can't forget this, plus or minus root 7. Now, you might go, oh, well, let's throw away the minus. No, we're not going to throw away the minus because this gives us 2 times. The bug is at 10 feet on the number line at these 2 times, plus minus root 7 seconds. You could also, if you don't like this plus minus, you could say root 7 seconds and negative root 7 seconds. They did not ask for an approximation. If they did, you would take out your calculator and go root 7, and that should be 2 point something. But they didn't do that. Okay, so that answers the first 2 questions. And you notice these questions are pretty much the same questions that we did in problem 1. These numbers are different, and the time interval's different. Let's go ahead and do this. What is the bug's displacement over the time interval from -2 to 2? This is where having that formula is really going to help you. So this is where the displacement happens to be f of the end time minus f of the beginning time. Okay, so notice it almost looks like we switch those. We do that for that, and then we have to know how to evaluate a function, f of 2. So we put 2 in there, 2 squared. 4 plus 3 is 7. I'll put parentheses around there, minus. We put -2 in there, we get -2, quantity squared is 4. 4 plus 3 is 7. 7 minus 7 is 0. Can that happen? The answer to that question is, it just did. Don't freak out, because it says, what is the bug's displacement over this time interval? 0 feet. What does that really mean? It means that at -2 seconds, the bug was probably standing at 7 on the number line. Now the bug was doing some movement in this time interval, but by the time we took a snapshot at 2 seconds, the bug was standing in the same position, so the displacement was 0. Displacement is just a snapshot from the first time to the second time. So he actually, just in those 2 times, it looks like he didn't go anywhere. He was not displaced. And if you're thinking about, like, what does this mean picture-wise, this is a parabola that opens up, and perhaps he was on one part of the parabola and then he passed the vertex, and at 2 seconds he was on the other part with the same height. But we don't have to actually draw the picture to do this. We'll just keep that as our answer. What is the bug's average velocity over the same time interval? Well, the average velocity is the displacement over the time. The displacement we found from the last one to be 0 feet. And the time, well, it looks like there's 4 seconds there. And so 0 over 4, when you have 0 on the top of the fraction, it's actually going to be 0, because we're saying what times 4 gives you 0. So it's 0 feet per second. The average velocity, 0 feet per second. Even though the bug was moving in that time interval, the average velocity, so sometimes he was going left, sometimes he was going right, and it averaged out to 0. That's why we will be studying this later. Instantaneous velocity is more satisfying, because you can actually see what was the bug doing, what was the velocity at a particular time, not a time interval. But this is what we have here. Now we could have done the other thing where we wrote, f of 2 minus f of -2, and on the bottom we could say 2 minus -2. It's the same result. What you're not going to see on this is total distance traveled, because we don't have the picture. Okay, we'll learn how to get a function that's written like this and do the total distance traveled in a time interval, but on a later bug handout. So E and F are just going to kind of be a repeat of what we did in C and D. What? A, B, C, D, E. Oh yeah, it's like losing it on my alphabet. What is the bug's displacement over the time interval -1 to 4? Okay, well, it's just like problem C. We're going to go f of n time minus f of beginning time. And this is just a calculation here. F of 4 is 16 plus 3, 17, 18, 19. Okay, so 19 minus, and we really don't need those parentheses there, but I'm doing this just because, I don't know, I don't want anybody to freak out. I want you to see this formula here. And then f of -1 is going to be -1 squared, so that's 1. 1 plus 3 is 4. So 19 minus 4 is 15 feet. So the bug's displacement within the interval -1 to 4 is 15 feet. What is the bug's average velocity over the time interval -1 to 4? Well, the average velocity, I didn't give myself much room on this paper, is the displacement over the time. The displacement is 15 feet. And the time there, actually, you can go 4 minus a -1 or figure that out. That's actually going to be 5 seconds on the time. 15 over 5 is 3. 3 feet per second. So there's the average velocity. And by the way, if we had a picture of this parabola and we connected the 2 points, the one that you find at -1 and the one that you find at 4, we connect those 2 points with a secant line. That secant line would have slope of 3. And same here, if you plot at the point at time equals -2 and plot at the point at time equals 2, you draw the secant line on that parabola and it would connect 2 points together on the parabola, and the slope of that secant line would be 0, which is horizontal. Once again, that's might be a little too much to say on this. For those of you who are trying to do just the minimum, make sure you know how to do those problems there. We're going to do one more problem that will help you with bug 3. And this last problem, this last problem is the bug's movement presented on a table. Okay? So the disadvantage of the table is, where was the bug at like 1.5 seconds? We don't know. I mean, so at 1 second the bug was at -2 on the number line, and at 2 seconds the bug was at 1. But 1.5 seconds, we don't know where the bug was. Now, so you might say, well, this is a dumb problem, but more often in the real world, we are given data points and we don't have all the points, and sometimes we have to kind of connect them together, and I mean, that's another class. But this is what we have. So let's go ahead and answer some questions. This does seem familiar. Where is the bug at 1 second? 1 second is time where they're asking for position. Here's time, and then this right here, this f of t, you can think of that as s. So here's the times, here's the positions. So we're going to look at time 1 second. And time 1 second is right here, so the position is -2. -2, and we've got to put our units. -2 feet. Now this says name one time that the bug is at 3 feet. Okay, so they give you 3 feet, they give you the position, and they're saying name one time. Now that's a weird way of writing that question. Well, we'll get back to that. Let's go ahead and find s equals 3. Do we have an s equals 3 down here? We have it right here. And when the position is 3 on this part right here, this is like a, an ordered pair, -1, 3. The output is 3. The time is -1 second. Now, the reason this question is asked in a weird way, instead of just saying what time is the bug at 3 feet, or what times, is because we don't know. I mean, maybe at 5 seconds the bug went back to 3 on the number line, or maybe at 1.5 that's where the bug is. We just don't have the data, so that's why it said name one time. Last two questions are ones that you'll probably hopefully feel more comfortable with. You can pause the video and see if you could do these ones on your own. Okay, so what is the bug's displacement over this time interval? I'm going to go f of n time minus f of -1. Okay, so f of, and that's the beginning time, f of 4 is 20 minus f of -1. f of -1 is 3. So this gives me 17 feet. What is the bug's average velocity over the time interval that we just did? Well, the average velocity happens to be the displacement over the time. The displacement, we just figured that out to be 17 feet. And the time looks like 5 seconds went by there. And so my final answer for this is 17/5 feet per second. And I just want to remind you, and I'll do this in purple, that the average velocity looks like this. F of 4 minus f of -1. That's the displacement. And the time is 4 minus a -1. So when we do this and we write this down, this is actually the slope of the secant line. If we were able to actually have a graph of these points, it's the slope of the secant line. So this completes bug number 3, and I'll see you on the next video.